Welcome to Lab 13. This week we're going to be talking about linear regressions, how to conduct them in PSPP, as well as how to generate predicted values in PSPP to save yourself some time doing some math. For this week you're going to need to access Lab 13 data, as well as the Lab 13 doc, which explains how to run regressions. For this week, we're going to be using the regressions example from class, where we are looking at how happiness affects health. We have our Dr. Farrell, who is trying to survey who sampled from 5 individuals, looking at how happy they were, as well as how many trips they took to the doctor in the past year. And he is trying to use this information to then predict something about trips to the doctor from happiness. And if he knows somebody's happiness ratings, can he guess how many trips they take to the doctor? So we're going to see this data in class as well as in our data set, so you can go ahead and open up Lab 13 data. In this data set, you will find 3 variables. That includes the happiness variable, the times to the doctor variable, as well as a subject number. And they all have labels. None of them have values because they're all continuous. And if we go to our data view, we will then see that we have the 5 subjects, 1, 2, 3, 4, 5, as well as the happiness scores and the times that they went to the doctor. Now, before we launch into running the regression, let's recap from last week the kinds of things we might want to know about these variables. For instance, we might want to know the descriptive statistics, in which case we just go to the descriptives. This will open up a window so we can find the means and standard deviation of both of our variables. Get rid of this minimum maximum. And when we open up our output, here we will see that the average happiness score was a 5 with a standard deviation of 3.54, and the times visited the doctor in the past year was a mean of 3 with a standard deviation of 2. Now, it's important to note here that these standard deviations are not the same that we got in class, and that's because these are using the -1. These are using the estimated standard deviation. PSPP is always trying to tell us something about the wider world, about bigger populations beyond our samples. But when we're doing correlations and regressions, we really only care about our samples, at least initially with the correlations. So these are not going to match what you calculate in class. We can't use them. But the means do match what we got in class. We also might want to visualize our data. We want to know how these 2 variables are related to each other. So we'd go to graphs and scatter plot. We'd put in our 2 variables, one as our x-axis, and for this we're going to choose happiness, and our y-axis, this time we're going to choose times at the doctor. Click OK. And this will open up a scatter plot that, again, isn't very visually appealing in PSPP. The ones that I created in class come from Excel, so you can figure out how to put those together, but that's beyond the scope of this course. But we can see that there looks like there is a negative correlation here, a negative slope here, that as we increase on happiness scores, there is a decrease in the number of times people visited the doctor in the past year. And it does look pretty strong and linear. Linear, negative, and strong. And then finally, we might want to actually calculate a correlation between our variables. So we'd go to Analyze, Bivariate Correlation, and we'd load in our 2 continuous variables. We could just determine whether we wanted 2-tailed or 1-tailed. We could tell it to flag the significant correlations, which is kind of standard practice. And we click OK. And here we'll find that there is a very strong negative correlation, a negative 0.99. As I've mentioned, this is the extreme end of the chart. You can only go between a +1 and a -1. So this is really close to as strong a relationship as possible. And we'll see that the p-value associated is a 0.001, a very small probability of this relationship existing, assuming that there was no relationship, of this finding appearing in our data, assuming that we should not have found a relationship. So very significant. But we now want to use this information. We know that these variables are strongly related to each other, but we want to be able to predict. We want, if we know somebody's happiness score, what can we guess about the times that they visited the doctor in the past year? So to do that, we are going to have to generate a best fit line through this scatter plot data to see what is the slope and where, if we had a score of 8 or 5 or 6, where would it triangulate, where would it fall on that line associated with a times visited the doctor in the past year. So to do that, we are going to go again to our analyze, because we are running an analysis of this data to learn something more. We're going to go analyze, drop down to the regression tab, and over to linear, because we are running a linear regression because the form of this line is a line, linear, line, it's all the same. When we open up this window, we're going to see all of our variables on the left-hand side, as well as two options for types of variables in our analysis. We have our independent and our dependent. We know the independent variable is usually associated with a cause, and the dependent is the outcome. In a regression, we are going to talk about these also as the predictor versus the outcome. So in the specific example we have in this class, we are trying to predict the times that will go to the doctor from happiness. So our happiness is going to be our independent variable, the thing that we are using to predict, and the times at the doctor is going to be our dependent variable, the thing that we are hoping to predict. Now we have statistics and save, but we're going to use those later on. For now, we're just going to leave it as is, click OK. And this will open up a chart, a series of tables down here. The first one we're going to see is the model summary. The model summary gives us the big picture image of how much are these variables related to each other. And for right now, the only variable, the only column you have to care about is this R value. This R value is very similar to the Pearson correlation that we calculated. In fact, when you run a regression with just two variables, that is one predictor and one outcome, this R value will look exactly the same as your bivariate correlation, except it will always be positive. You see, our correlation is a negative 0.99, but here is just a 0.99. Now, later on in future courses, you might have more than one predictor variable in what's called a multiple regression, and this R will change. It won't match a bivariate as much, but for right now, when we have just one predictor variable of happiness, this R is going to match except be positive. It's the absolute value. We're also going to see in this table the standard error of the estimate, which we will get to a little bit later in this lab, but it is an important piece of information. And we have the R squared, which is about variance. This is slightly more advanced than anything we're going to cover in this course, but this represents how much of the times visited the doctor is explained by happiness. So it's the amount of variability in your dependent variable that is explained by your independent variable. So that's the R squared. The next table you'll see is an ANOVA. This ANOVA is going to tell us whether this best fit line actually is a good one, whether it fits pretty well or not at all. And this is going to look like the one-way ANOVAs that we have calculated in this course so far, just a couple weeks ago. But it's going to have a reduced number of degrees of freedom, pretty limited, and there's going to be a slightly different calculation for the sum of squares. I'm not going to go into the math of how these are all generated, but you do want to look at the F statistic and the significance, or the p-value here. And if this is significant, it means that this line through the data is a good estimate. It basically means that the dots fall close enough for this line to this line for the line to be usable. The amount of error that is coming off of this line is not so big that it's useless. So basically it says this is a good tool. This regression is going to be a good tool. If this was non-significant, then we might throw it out and say, hey, we can't actually predict anything, it's not useful, but as long as it is significant, we can continue. So if we see that this ANOVA is significant, we can continue down to this coefficients, this third option here. This third one is what gives us the regression equation. There's a lot of information here, but the only things you really need to look at are the stuff in the B column. We learned in class that the equation for the predicted y is going to be bx plus a. Well, PSPP represents this all as b's. Here in this happiness score, we will see the amount of change in our y value based on our x, based on our happiness score. So here, our b for the change in y based on x, based on our happiness score, is going to be a change or a decrease of 0.56. So what this means is every increase of 1 in happiness results in a decrease of 0.56 in our times visited the doctor in the past year. It's also going to give us our constant or our intercept. And this is saying that the constant is when x equals 0, when there is no happiness score. So when x equals 0, that is our constant, is going to be our intercept of 5.8. And as we recall, our equation is that y hat equals negative 0.56x plus 5.8. Before we move on, we should also review the syntax for a regression. Here we have the keyword is regression, and we're going to put the variables, the independent variables. So the predictor is going to be under this variables line, and in our case, that's just going to be the happiness, that single variable. Then we're going to have the dependent variable line, where we put the outcome we care about. This method enter is a standard, don't worry about changing that. And then we have what statistics do we need. So this is going to ask for our coefficients, which are these down here. It's going to ask for our R, which is this model summary, R and R squared. And it's going to ask for the ANOVA, which tells us whether our best fit line is in fact a good line at all. All right. So we have generated our best fit line equation. We know that it's a good line, but we also know that there's some amount of error off of this line, that the dots don't match perfectly. We also know that if we asked about what the y-score would be, assuming that x equaled a certain number, such as 5, the result we get is just an estimate, but it has some range of variables, some range that it is inaccurate. And so what PSPP gives us is that standard error of the estimate here. This is the average amount that our observed data differs from our expected scores. But we might also be curious how to get those predicted values, those expected. So if we want to get our expected values, we can do that very easily by going to Analyze, Regression, Linear Regression, just as we did before. But this time we're going to click the Save button. And when we click the Save, it's going to give us the option of selecting predicted values. Click Continue, and you can click OK. And what this is going to do in your output is give you the exact same thing. In fact, nothing changes except for now you have the syntax code of save equals pred, or for predicted. But what you actually get when adding that into your syntax is it takes the number that you scored in your x variable, in this case your happiness, and it plugs it into the equation. So if the individual got a score of 1, what do we expect was the score on the number of times they went to the doctor? If an individual scored a 3 and we trace that, not looking at our actual observed data, but just using our equation, what do we expect they got on number of times visited the doctor? Same thing for 4, 7, 10. We get all of these numbers. So these are what the data should have been, what we expected, if it fit our line perfectly, compared to what it actually was. And as you'll see, there's slight differences. Here we have a 5 was the actual, but a 5.24 was the expected. A 4 and a 4.12, a 4 and a 3.56. So there's slight differences between these. And so here's where we see our error. In fact, if we wanted to do our math a little bit more, we could calculate each of the deviances. So we might go to Transform, Compute, and we could tell it that we want to take our actual variable, our y variable, minus our expected variable, and this would give us our difference score. We could type in the target. So here we see that we have a difference of minus 2.4. There was a error of negative 2.24. Whereas here we have a large increase. So this one was above our line, whereas these ones were below the line. So 3 below the line, 2 above the line, which if we look back at our graph, that's exactly what we have. We have 3 points that were below the line and 2 points that were above the line. If we wanted to, we could even go back to our data, go to compute, and we could calculate a squared difference, which would be the difference times the difference variable. And we would get this difference squared. And if we summed up all of these variables here, in fact, let's go to Analyze Descriptive Statistics, Descriptives. Let's ask it about the difference squared, and we're going to ask it for a sum this time. And when we're back in this output, we will see that the sum here is a 0.32, which we calculated ourselves as the sum of squares for the residual. If we divided this number by our degrees of freedom, or our n minus 2, and then square rooted, then we would get this standard error of the estimate. We get that exact same number. So that is just the step-by-step process of how we can compare. So this week what we've covered is a review of how to do those scatter plots and correlations. We've also shown you how to calculate a linear regression and how to find those B, A, and C, the R values, those model statistics. We've shown you where the standard error of the estimate lies and what that ANOVA kind of means in broad strokes, as well as showing you how to generate predicted values in PSPP so that you can then transform to see where the data points deviated from this best fit line. In this week's lab assignment, you will be entering data similar to that from last week with correlations, and then running regression lines and calculating predicted values based on those. Best of luck.